Hi, my name is Amelia Kopp, and this is the Physics 2211 Lab Number 1. To begin with, we need to discuss the fundamental laws of physics applied in the real world. First is the momentum principle, also known as Newton's second law of physics, which tells us that an object in motion will continue in motion unless acted upon by an unbalanced force. In ideal conditions, meaning there is no friction, an object with an initial velocity or momentum will continue that motion with the same magnitude of values for an infinite time, where time is represented by the variable t. This continues unless the object is acted upon by an unbalanced force that could cause acceleration or deceleration. Basically, when the net force is zero, which is the ideal condition, the object's momentum will continue constantly due to the conservation of momentum. The Lab 1 experiment discussed today compares a computer model to a real-world scenario, where I use an object moving with constant velocity. We use the initial conditions and then GlowScript, which uses Python language to create a computational model of the motion of the object. I then compared those predicted values to the values gathered by the experiment. These are the relevant equations and formulas used in GlowScript to calculate the predicted values of motion for the object, as well as the initial conditions used to get my values. First, I use Newton's second law and assumed there was no friction, which makes the net force zero, as seen here. Then I used the calculated slope of my experimental values, which is gathered using tracker, as my velocity vector, as seen here, by the 1.048. I then used the position update formula to continuously update the position of the object based on this velocity, as seen by this line of code here. Here's the video I used, and as you can see, there were very few discrepancies in my technique for gathering the position of the object frame by frame. I assume this will continue as we practice labs in this course. Here's a graph of both the predicted and real-world values gathered during this experiment. First, I gathered the real-world values from the video before and then used the line of best fit slope in the GlowScript, as mentioned before, to graph the predicted values as seen in blue. Because of the careful use of tracker during the experiment in gathering the positions of the object over time, both of my R values are equal to 1, meaning the relative error between the line of best fit and the actual data values are very small. My observations include 3 main points. First is that both lines have a linear slope, meaning the object, when given the initial velocity and assuming no net force, moves at almost a constant velocity. And the data, while not perfectly linear, was linear enough, and the bottle moved with a slower velocity than the model predicted, as seen here by the comparative values of 1.0436 and 1.048. Next is that the difference in the graphs and data are due to user error. As seen in the video, the values gathered by tracker gave the position a negative value due to where the y-axes were oriented to the object. That is why it is more important to pay attention to the slopes than the actual values of position versus time. Next are the concept questions. Question number 1. What if you were asked to analyze your video data in tracker? You made a choice of the orientation of the axes. How your results would change, and how they would remain the same if you were to flip the axes, meaning if the positive x and negative y were interchanged. I used my predicted values to answer this question, as seen here. This represents the values that I actually collected in orange, and the blue represents if I had switched the orientation of the x-axis. All that would happen was that my positive y values, the position, would then become negative position in relevance to time. The next question: what does it mean that your observations can be predicted well by your computational model when you set the net force equal to 0 in your model? Is it possible for you to say how many pushes and pulls, meaning how many forces, are added together to give 0 net force in the case that you observed? My answer is that there is no way to tell the exact amount of forces required to make the net force 0, meaning no friction, for this experiment. We do know, however, that since the velocity is